In this lesson, we'll study the notion of an isomorphism, which is a way of saying that two groups are essentially the same. But first, let's start with an example. We'll let G be a group element with order 6. So there's nothing special about 6 here, but just to get something concrete. We'll consider the cyclic group bracket G. Recall that this is the set of all integer powers of G. So we have all the positive powers of G, negative powers of G, G to the 0, which is the identity element. So here are some tasks to get us started. First, please find the smallest positive integer k such that G to the 45 is equal to G to the k. Part B, same as above, but with G to the minus 2. And then part C, find the distinct elements of bracket G. And for all of these, do keep in mind that the order of G is 6. So if you could pause the video and give these questions a try, and we'll go over them in a moment. All right, well, part A, k equals 3, because G to the 6th is equal to the identity element. So we can treat this exponent here mod 6. And same for G to the minus 2. If we treat that mod 6, then we get k equals 4. And then the distinct elements of bracket G happen to be the following 6 elements. G to the 0, which is the identity, G to the 1st, 2nd, 3rd, 4th, and 5th, and then G to the 6th is back to the identity element again. So those 6 elements are the distinct elements of bracket G. Now please pause the video and work on day 16 classwork. Then afterwards, we'll go over some of the problems and ideas. In the classwork today, we looked at an element of order 6, and then we considered a cyclic group generated by that element, bracket G. And we saw that we compared the groups Z6, which is an additive group, and then the multiplicative group bracket G, and saw that their elements match up. Now, what do we mean by that? Well, here are the 6 elements of Z6, 0, 1, 2, 3, 4, 5. And then here are the 6 elements of bracket G. G to the 0, G to the 1, G to the 2, G to the 3, G to the 4, G to the 5. And they pair up nicely, those elements match up. So for instance, the element 3 in Z6 matches up with the element G to the 3rd in bracket G, and so on. Now, not only do the elements match up, we also saw that their operations match up, even though Z6 has addition as an operation and bracket G has multiplication as an operation. Now, how do those operations match up? Well, let's look at some examples. So in Z6, we have 3 plus 5, which is 8, mod 6 is 2. So green plus silver is maroon. In bracket G, we have G to the 3rd times G to the 5th, which is G to the 8th, but G to the 6th is the identity, so that reduces to G to the 2nd power. Once again, green times gray equals maroon. And so, informally, addition in Z6 feels like multiplication in bracket G. Even though we have 2 operations that are different, they feel very similar to each other. And so because the elements and the operations of those 2 groups match up, we say that the groups Z6 and bracket G are isomorphic. In other words, they're essentially the same group. And so now in the next few slides, let's give a more precise definition of what we mean by isomorphic. Now, to make the notion of an isomorphism or isomorphic groups more precise, let's define a function theta from z6 to bracket g, where theta of a equals g to the a for all a in z6. So for example, we have theta of 3 is equal to g to the third power. And do keep in mind that we're still working with order of g being 6. So before we said that the elements of z6 and bracket g match up, but let's make that more precise using this function theta that we have. So rather than saying that the elements in those two groups match up, what we really have is that theta is a bijection. In other words, a function that's both one-to-one and onto. And we can see that visually here. And what this does is that this function theta specifies how these elements match up. So for example, we see that 3 matches up with g to the third because theta maps 3 to g to the third power. And so theta being a bijection is a more precise way of saying that the elements in those two groups match up. Next, let's consider this notion that the operations of z6 and bracket g match up. And we like to use our function theta to make that notion more precise. So to do that, let's consider a pair of elements in the domain, 3 and 5 in z6. And we can work with those two inputs in a couple of different ways. So first, we could add them in z6 and then apply theta to the sum. So we add them first in z6 as follows. We get 3 plus 5. And then we can apply theta to that sum. And if we do that, we get theta of 3 plus 5, also known as g to the 3 plus 5th power. Now, alternatively, we could also apply theta to each of 3 and 5 separately first. And so we get theta of 3, and then applying theta to 5, we get theta of 5 right there. And then multiply, because we're in bracket G, multiply those two outputs in bracket G. And I claim that if we do that, that product is the same result that we got in the earlier calculation. So let me just write down the equality and we'll talk about why that's true. So that equals theta of 3 times theta of 5. Now, why is that true? Well, theta of 3 plus 5 we saw was the same as g to the 3 plus 5th power. Theta of 3 times theta of 5 is g to the third times g to the 5th. And we know from the law of exponents that those two are the same. And so we end up with this beautiful relationship right there. Theta of 3 plus 5 is equal to theta of 3 times theta of 5. And that really captures this notion that addition in Z6 feels like multiplication in bracket G. And so that's the more precise way of saying that the two operations match up. Now let's generalize. So suppose we have two groups G and H with their operations star G and star H. Typically, we assume by default that group operations are multiplication. By using these notations, we are specifying which multiplication this is. So this is the operation of G, and this is the operation of H. A function theta from G to H is said to be an isomorphism if two properties are satisfied. One, theta is a bijection, one-to-one and onto. This ensures that the elements of G and H match up. And then second, well, we have to make sure that the operations of G and H match up. And this is the generalization of what we just saw in the previous slide. We say that theta is operation preserving, or preserves the operations of G and H, if the following equality holds for any pair of elements in G. So once again, this means given those two elements A and B, we can either multiply it inside G, that's the star G right there, multiply them inside G and then apply theta. That's the expression theta of A times B. Or we can apply theta to them individually and get theta of A and theta of B, and then multiply them inside H. That gives us theta of A times theta of B, where this multiplication is occurring in H. And theta being operation preserving means that those two processes yield the same result. This is a more precise way of saying that multiplication in G, or the operation in G, really feels like the operation inside H. So that's the definition of theta being an isomorphism. And when we have that isomorphism, we say that the group G is isomorphic to H. And here's a shorthand, which means G is isomorphic to H. And really that means that those two groups are essentially the same group because their elements match up and their operations also match up. So isomorphic groups mean that they're essentially the same group. Here's a theorem involving an isomorphism. So it states that let theta from G to H be a group isomorphism. And what we mean by this is that G and H are groups, and theta is an isomorphism between the two. So that's what we mean by group isomorphism. And the statement is that if H is commutative, then G is also commutative. Now, before we think about why this is true, from an intuitive perspective, the fact that theta is an isomorphism from G to H means that G and H are essentially the same group because they're isomorphic to each other. And that means that if one of them is commutative, the other one better be commutative as well. So that's the kind of the intuition behind this theorem. Now, before we actually write down our proof, we have some visual that hopefully can give us some direction on how to go about proving it. So we have G here, the domain of theta, and then we have H, which is the codomain, and we know H is commutative. And we're trying to show that G is commutative, so we have a pair of elements A and B, and we'd like to show that A times B equals B times A. And right now I kind of drew those two products separately, but we want them to be the same. But now let's compare what's happening inside H. Once again, we have this isomorphism between G and H. So element A in G corresponds with theta of A in H. Element B corresponds with theta of B. And because H is already known to be commutative, we can say that theta of A times theta of B is equal to theta of B times theta of A. And so these two elements can be multiplied. Doesn't matter the order, they give us the same product. But what else do we know? Well, theta, being an isomorphism, is operation preserving. And so this expression here, theta of A times theta of B, equals theta of A times B. In other words, we can multiply A and B first in G and then apply theta, or apply theta to them individually and multiply them in H, and we get the same result. Likewise, theta of B times theta of A is equal to theta of B times A. And so we know that theta of AB is equal to theta of BA. And the elements theta of AB and theta of BA do match up with AB and BA respectively. So if these two are the same, these two should be the same as well. And so that's the intuition behind our proof. And so in the next slide, let's write this down carefully and turn that into a complete proof. So now let's turn this into a complete proof. So here's our theorem, and I've even written down our first sentence, which is our hypothesis. So we'll assume that H is commutative, and we must show that G is commutative. So in order to do that, we'll start with two elements in G. So we'll let A and B be elements of G. And we have to show that AB equals BA, so let's write that down at the very bottom. So thus, A times B equals B times A. And I like to, in this proof, be very explicit about where these multiplications are taking place. So rather than just writing star here, I'll write star G to indicate that for these products, that multiplication is taking place inside G. And so that's our final goal. Now, we saw in our picture that we use the isomorphism theta to eventually show this equality. So let's say take the left-hand side and apply theta to it. So we have theta of A times B, where that product is happening in G, is equal to theta of A times theta of B, where this product is happening inside H, and the reason is because theta is operation preserving. Operation preserving. Now, just a quick word about this reasoning here. I could have said, since theta is an isomorphism, and that would have been true, but the phrase theta is an isomorphism really packs a lot of information. Theta as an isomorphism means theta is a bijection, which means it's one-to-one and onto, and also it's operation preserving. So rather than saying something very general and a little bit vague like theta is an isomorphism, we can be more specific about what aspect of an isomorphism we used, namely theta is operation preserving. So let's do that in these isomorphism proofs. Now we can do the same thing with B times A. So we'll say similarly, theta of B times A is equal to theta of B times theta of A, keeping track of where these multiplications are taking place. And then because h is commutative, these two expressions, whoops, do it in yellow, are equal to each other. So let's write that down. Since h, not theta, h is commutative, we have theta of a times theta of b, where that multiplication is taking inside h, which is a good thing because we're using the fact that h is commutative. So that's equal to theta of b times theta of a. And therefore, because these two yellows are equal to these two greens, we can say that the greens are equal to each other. And therefore, theta of a times b is equal to theta of b times a. And we can color code these as well. So these are the yellows that we already know are equal to each other, and therefore their corresponding greens are also equal to each other. Now we've established that theta of a times b equals the theta of b times a. How do we go from there to saying a times b is equal to b times a? Well, we once again use the fact that, and I'm going to make a little space here, that theta is an isomorphism, but more specifically, we say thus, since theta is 1 to 1, that's what allows us to say that if these two outputs are equal, then the inputs had to have been equal. So since theta is 1 to 1, we conclude that a times b equals b times a. And so let's move this up a little bit higher. And so once again, let's be explicit about what aspect of an isomorphism we're using. Here, we're using the fact that theta is 1 to 1. And so that's the end of this proof, and also the end of this lesson. So I will see you next time.